continue our discussion on digital systems, and today's topics are inverse systems, stability criterion, differential equations, FIR and IIR, and recursive and non-recursive. Although I have put a large canvas, we shall uncover only that part which we can do comfortably. In the last lecture, we had first clarified a question about time invariance, and the example in question was an upsampler. We showed that even if the waveform is preserved, the number of samples by which the output is delayed is not the same as the number of samples by which the input was delayed. Then we introduced the terms impulse response and step response and commented that the two are very intimately related to each other. We illustrated impulse response and step response by various kinds of accumulators. We also took the example of an upsampler and an interpolator. Then by simple reasoning, we derived the convolution equation for an LTI system, and we said that if y of n is the output to an input x of n, then all you have to do is xk multiplied by hn minus k and sum it up from k equal to minus infinity to plus infinity. For special cases, the limits change. For example, if x of n is causal, then the lower limit becomes 0. If x of n is causal and h of k is also causal, then the lower limit is 0 and the upper limit becomes small n. Agreed? And then we took an example of calculation of the convolution sum by the usual graphical method, that is shifting one step at a time, either to the right or to the left, depending on which particular sample of the output you wish to compute. And I also introduced a trick by which all this graphical step-by-step procedure is not needed, and that was simply the same process as that of arithmetic multiplication, except that there is no carry, and except also for the fact that you must indicate, you must keep track of your reference, that is the pivot y of 0, and that occurs when the sum of the indices of x and h is equal to 0. So, x0, h0, if it is x of minus 1, the corresponding h term must be h subscript 1, and so on. And then you go to the right, one step you get y of 1, two steps y of 2, and so on. I would like to introduce to you a third trick, which is equivalent to the trick that I mentioned earlier, but it is interesting from the point of view that history of DSP is prominently marked by this technique. The geophysicists were the first ones to use DSP without knowing that they were doing digital signal processing. What they did was they also manipulated numbers, multiplication, addition, and so on and so forth. And they said, suppose you have what was our sequence? Let's take the same example. X minus 1, x0, x1, and we had x2. This was one of the sequences. All right. The geophysicist said that instead of writing it as a sequence, let's write it in the form of a polynomial, okay, where the power of the variable, they introduced an arbitrary variable. Let's call this variable as p. That is, what we do is we write this sequence. Please follow this carefully, how how intelligently these people hit upon what is now known as Z transform. They didn't know what is Z transform. Z transforms came much later, 50s, whereas these people were doing it in 40s. They said we will convert this into a polynomial, and we shall say x of p is x of minus 1 p to the power minus 1. The power of the variable indicates the position of the sequence. This is of course n equal to 0. All right. Then x0 p to the power 0, which is 1, plus x1 p plus x2 p squared. They were also required to do convolution for some geophysical parameter, for finding some geophysical parameter of interest and importance. Similarly, our H sequence was H of minus 2, H minus 1, H naught and H1. They said we will not store 4 numbers, but we will store one polynomial. We will write one polynomial, and they called it H of p as H of minus 2 p to the power minus 2. The power of the variable indicates the position of the number in the sequence, plus H minus 1 p to the power minus 1 plus H naught plus H1 p. And they said in order to find the convolution summation, they didn't use the word convolution, or maybe they used the term convolution, yes. To find the convolution, you multiply xp by hp. You see what you get. xp hp is equal to x minus 1 p to the minus 1 plus x0 plus x1 p plus x2 p squared. This multiplies h minus 2 p to the minus 2 plus h minus 1 p to the minus 1 plus h naught plus h1 p, and find out the result in terms of powers. So this will also be a polynomial in terms of powers of p. For example, p to the minus 3 will be obtained by multiplying this term by this term, and this is the only term. So you get h minus 2 x minus 1 p to the minus 3 plus then p to the minus 2 terms. H minus 2 multiplies x0, h minus 2 multiplies x0, then plus h minus 1 multiplies x minus 1, you get p to the minus 2, x minus 1 plus h naught multiplies
h naught x minus 1.
H naught multiply, I want p to the minus 2, that's all, okay, p to the minus 2 plus p to the minus 1 h minus 2 x1, okay, h minus 2 x1 plus
h minus 1 x naught,
h minus 1 x naught plus
h
naught
x minus 1.
x minus 1, and that's all. That is p to the minus 1, and so on. If you continue this, then you see that this is nothing but our y of minus 3, this is nothing but y of minus 2, this is nothing but y of minus 1, and you get all the terms in the sequence. Is the process clear? What we are doing exactly is that arithmetic multiplication, except that we are not putting in the form of a table, but we are doing it in this. This is how the geophysicists used to compute convolution, and this is also a trick. Instead of this graphical shifting where you make one mistake and your total result is shattered, this is also a trick which can be exercised. And as you can recognize, those of you who have an acquaintance with Z transform, this is nothing but Z transform, except that instead of the variable Z inverse, we have used the variable P. If we use P equal to Z inverse here, we get exactly the Z transform. So you can compute convolution by at least 3 techniques: graphical, the arithmetic multiplication, or the multiplication of 2 polynomials. And if you are in doubt, check it by at least one more method. Okay, this is another trick. I have not completed this example, which I hope you would be able to, and you can show that it's exactly the same. We next talk about inverse systems, inverse digital systems, of course. A system whose impulse response is h1 of n is said to be the inverse of another system whose impulse response is h2 of n if and only if the convolution of h1 of n to h2 of n is equal to delta n. If the convolution gives you a unit impulse, then the two systems are said to be inverses of each other. And the reason is very simple, that if the output of h1n is connected to the input of h2, and if your input is x of n, then the output should also be x of n, because x of n convolved with delta n is simply equal to x of n. Right? You write that summation equation, it exists only for n equal to 0, and therefore you get x of n star delta n equal to delta n. So two systems h1 and h2 are inverses of each other if their convolution gives rise to a unit impulse function delta n. Let us take an example of an inverse system. Suppose we take the accumulator y of n equals to summation k equal to 0 to infinity x of n minus k. This is an accumulator. We wish to find out its inverse. Okay. So the first thing we do is we find h of n as equal to summation k equal to 0 to infinity delta of n minus k. Simply substitute delta for x, all right, and you know that this is equal to u of n, the unit step function. So if an inverse system exists, and its impulse response is h prime of n, then h of n convolved with h prime of n should be equal to delta of n. In other words, h prime n convolved with summation delta n minus k, k equal to 0 to infinity, should be equal to delta n. But what is this equal to? H prime of n convolved with delta of n minus k is simply h prime of n minus k, and therefore this equation gives me k equal to 0 to infinity h prime n minus k equal to delta n. Let's expand this equation. I'll write it again. K equal to 0 to infinity h prime n minus k equal to delta n. I start from k equal to 0, so I get h prime n plus h prime n minus 1 plus h prime n minus 2 and so on up to infinity is equal to delta n. Let us put a few values for n. H prime 0 plus h prime of minus 1. If we assume that the system is causal, what does causality mean? H prime n is 0 for n less than 0. Therefore, h prime 0, h prime minus 1 is 0, minus 2 is 0, all other terms are 0. And what is the right hand side? 1? delta of 0 is 1. Then n equal to 1, I get h prime 1 plus h prime 0. Then if n is 1, h prime minus 1. So, all the rest of the terms are 0. So, this should be equal to 0 because delta of 1 is 0, which implies that h prime 1 is equal to minus h prime 0, that is equal to minus 1. What is h prime 2? Put n equal to 2. I get h prime 2 plus h prime 1 plus h prime 0. Once again this is equal to 0, right? Delta of 2 is also equal to 0, but we have already shown that this is equal to 0. Therefore, h prime 2 is equal to 0. And if you continue, then for all values of n greater than equal to 2, the impulse response is 0. Therefore, h prime n equal to 0, n greater than equal to 2. In other words, h prime n consists of only two samples, one at n equal to 0 of amplitude 1 and the other at n equal to 1 of amplitude minus 1. Therefore, my final result is that h prime of n is equal to delta n minus delta n minus 1. That is it. We have found in a very simple manner the inverse of an accumulator whose impulse response is a unit step. The inverse may or may not exist. It does not exist if the inverse system is unstable. In other words, if what is the condition for instability? Bounded input does not lead to bounded output. Okay. Now, this was the case of cascade, that is H1 was cascaded to H2. If I have a parallel interconnection H1 of n, system H1 of n is in parallel with H2 of n, then this is equivalent to a single system in which the impulse response is H1 of n plus H2 of n, because there is parallel processing. This system is very important in practice because it enhances the speed of processing. When H1n is dealing with the signal, simultaneously H2n is also dealing with the same signal, and therefore if a complicated system, if a high order system is broken up into simpler systems and connected in parallel, then the speed of processing goes up. So, parallel processing is important for digital systems, and wherever possible, instead of serial or sequential processing, one resorts to parallel processing.
What can we say about the stability of the system?
What can you say about the stability of the system? That is a very good question. In a parallel system, if H1n and H2n are individually stable, is there a possibility that the system becomes unstable? No. Suppose one of them is unstable, the other is not, then the whole system is unstable because it does not know what H2n is doing. Isn't that right? They are independent of each other. So, if this goes wild, the whole system goes wild, because wild adds to sanity. Sanity plus wild is wild. Okay? Insanity. Very good question. Stability, as I have defined, is bounded input, bounded output. For an LTI system, stability can be characterized by its impulse response h of n. And the theorem is, I will first state the theorem, then prove the necessity as well as sufficiency. Very simple theorem. It simply says that a linear time invariant system, an LTI system, is stable if and only if the quantity capital S defined as summation of absolute value of h of n, where n goes from minus infinity to plus infinity, is bounded, is less than infinity. Another way of saying the same thing is that the impulse response is absolutely summable. The absolute summability of the impulse response ensures stability. So we prove it from the forward direction and also in the reverse direction. That is, step 1, we prove that if S is less than infinity, then magnitude, absolute value of y of n is also less than infinity. This is the first thing that we prove, and it is very simple to prove, because your y of n is nothing but summation x k h of n minus k, or equivalently, I am not putting the summation limits, they are implied, I do not want to write it again and again, or equivalently we can also write y of n, as you know the operation is commutative, we can write x of n minus k h of k. We are talking of BI-BO stability. So, let x of n be bounded by some quantity Bx less than equal to, which is less than infinity. Then y of n, magnitude y of n shall be less than equal to the summation magnitude x of n minus k magnitude h of k. Why is it less than equal to? Because some of these products may be negative, alright. Some of these products may be negative, we are taking the positive value, therefore it is less than or equal to, alright. If they are real numbers and all of them are positive, all products are positive, then we do not have to use the absolute sign. Absolute sign we are using because x of n minus k as well as hk may be either positive or negative. So, this is the upper bound, and therefore, this is less than equal to, suppose we replace each x n minus k by bx, by its upper bound, then I can take bx outside and then I get summation h of k. Obviously, this is equal to S, and therefore, if S is less than infinity, then S Bx is also less than infinity. In other words, we have proved that if Hk, Hn is absolutely summable, then the system is BI-BO stable. Now we have to prove it conversely. What is the converse statement? That if the output is bounded, if y of n is less than infinity, if the absolute value of y of n is less than infinity, with x of n bounded, then S should be less than infinity. In step 1 we assumed S less than infinity, in step 2 we assume output is bounded and prove that S is less than infinity. So, let the output be bounded. Step 2, the converse statement, let output be bounded by some bound by less than infinity, then absolute value of y of n, no, let us take y of n directly, I do not have to take absolute value, it is summation x n minus k h k, alright. Now, I told you that 1000 examples is not sufficient to prove anything, but one counter example is sufficient to destroy it. All we have to do here is to take one situation. This should be true for all situations, all right. Let us take x of n minus k as equal to plus 1 when hk is positive. That is, we choose an input which is either plus 1 or minus 1. It is equal to minus 1 if hk is negative. The corresponding samples, okay, depending on what hk is, we choose our x of n minus k. We choose it either plus 1 or minus 1. Then what does this become? Under this condition, y of n becomes magnitude y of n becomes, each of these terms will be positive now, and since x of n minus k is taken as 1, all right, plus 1 or minus 1, this is simply equal to summation hk, which is equal to s, and therefore if y of n is bounded, s should also be bounded. So it is a proof of the theorem that an LTI system is stable, BIBO stable, if and only if h of n is absolutely summable. An absolute summation simply means summation of the absolute value over all values of n is less than infinity. We shall use this a little while later to prove something else. A digital system in general is described by a difference equation, and we have encountered a number of difference equations. For example, y of n minus y of n minus 1, alpha y of n minus 1 equal to x of n is a difference equation. Y of n equal to xn plus x of n minus 1 plus x of n minus 2 is also a difference equation. This is a recursive difference equation, and this is a non-recursive. I have explained the terms recursive and non-recursive. This uses past value of output, so feedback it does not use. The second one does not use. This is recursive, this is non-recursive. In general, an LTI system is described by an equation of this form. In general, these are first order equations, this is second order. In general, an LTI digital system is described by an equation of this form: yn plus b1 yn minus 1 plus b2 yn minus 2 up to, let us say, bn yn minus n is equal to a1 x of, let us put a0 x of n plus a1 x of n minus 1 plus etc. There is no binding or obligation for x terms going up to capital N. It might end at capital M, which is less than n or which is greater than n. So we say a m x of small n minus capital M. If this is the situation, you notice that I have written it in a particular form. I have put the first term, the present output that I want to compute, with a coefficient of 1. If it is not, if it comes with a coefficient b0, we shall divide throughout by b0. So it is always possible to write it in this form, and we shall always do it. It is a matter of discipline which we shall follow. Now, the order of the system in such a difference equation, the order of the system is the higher of the two quantities capital M and capital N, order equal to higher of m and n. Whichever is higher, we'll call that as the order of the system described by this difference equation, or order of the system, or order of the difference equation. Okay. Given this difference equation description of a system, and given the fact that it is causal, then you can compute y of n for any n greater than equal to some quantity n0, provided initial conditions on the system are given prior to n equal to n0, right. It is only after that, after n0. So, all conditions prior to n0 must be known, then you can compute y of n. That is, you can find a solution to the difference equation, and on this topic, solution of difference equation, we shall spend a little time. Given a difference equation, for y of n as a function of x of n and y of n minus I, let us say, okay, it is a linear equation. There are no products of x of n and x of n minus 1. There are no products of x with y. It is a linear equation. Given this, the solution to the difference equation, exactly like differential equation, consists of two parts, namely a part which is called the complementary function. The complementary function is the solution to the given equation with x of n equal to 0, that is, with x of n minus 1, n minus m, all of them equal to 0. This is the complementary function. In the differential equation, you put the right hand side equal to 0. It is exactly the same way, and added to a particular solution. Particular solution is the solution with x of n. All right. Now, whenever you solve an equation with right hand side equal to 0, there would be some unknown constants. Okay, there would be some unknown constants, and these constants have to be found out from the initial conditions. If it is a second order system, then you require 2 initial conditions. If it is a third order, then you require 3 initial conditions. Okay. From the initial conditions, you can find out the constants in yc of n. Yp of n shall have no constants. Yp of n shall be completely determined from the given difference equation. Okay. And the constants have to be found out not before adding the particular solution. It is to be done after adding the particular solution. This point must be remembered. After solving the so called homogeneous equation is the equation obtained by putting x of n equal to 0 in the given difference equation. That is called homogeneous. For example, the homogeneous equation in our case shall be yn plus b1 y of n minus 1 etc. plus bn y of n minus capital N equal to 0. This is the homogeneous equation. And the solution to this equation we shall call this y sub c of n. The name for it is the complementary function, exactly like differential equations, linear differential equations. Y c of n in general shall contain capital N number of constants, capital N constants, and these constants have to be evaluated from initial condition, but not at this stage. You must first find out what is yp of n, add yp of n to yc of n, then put the initial condition. This step is extremely important. Okay? Initial conditions are called for only after you find the particular solution and add it to the complementary function containing capital N number of unknown constants. Okay? Do not evaluate the constants before adding the particular solution. The constants appear like this. If you have an equation like y of n plus b1 y of n minus 1 plus etc. plus bn y of n minus capital N equal to 0, then the complementary function is obtained by trying a solution, of the form yn equal to lambda to the power n, some quantity raised to the power n. N is the variable. In the analog or continuous time case, you say e to the power mt or e to the power mx. This is also an exponential. Lambda can always be written as e to the power m. Agreed? This is also an exponential, but we do not have to show it explicitly. Our lambda to the power n is good enough. If you put this in this equation, then you get lambda to the power n plus b1 lambda to the power n minus 1 and so on, plus bn lambda to the power n minus capital N equal to 0. From this, obviously you can cancel lambda to the power n from both sides, provided it is not 0. If lambda to the power n is 0, then of course you have no equation. No equation, no solution, right? So lambda to the power n can be cancelled from both sides and you get one. No, what do you get? If you cancel lambda to the power n and multiply by lambda to the power capital N, okay, lambda to the n cancels, multiply by lambda to the power capital N, then the last term would be bn and the first term would be lambda to the power capital N. So the next term would be b1 lambda to the power n minus 1 plus etc. plus bn. This will be equal to 0. The left hand side is called the characteristic polynomial of the linear time invariant system, characteristic polynomial of the system, and the roots of this characteristic polynomial or the solution of this characteristic equation. If the characteristic polynomial is equated to 0, then you call this equation is called the characteristic equation. The roots of the characteristic equation or the zeros of the characteristic polynomial are the so called eigenvalues, and it is a fundamental theorem of algebra that if you have a polynomial of degree n, then it has n number of roots, okay, and therefore let the roots of the characteristic equation be lambda 1, lambda 2 and so on up to lambda n. There will be capital N number of roots, we call them lambda 1, lambda 2 and so on, and therefore we had tried the solution lambda to the power n. Lambda can take any of these values and therefore our solution yc of n, the complementary function, would be of the form alpha 1 lambda 1 to the n plus alpha 2 lambda 2 to the n plus etc. plus alpha n lambda n raised to the power n. This is small n. This will be the complementary function or the solution to the homogeneous equation, and this is where these constants occur, alpha 1, alpha 2, alpha n. It is very tempting at this stage to put the initial values, that is y of 0, y of minus 1, y of minus 2 and so on, or y of 0, y of 1, y of 2 and so on, to find out this, but this temptation must be done away with, okay, because you shall end up in a wrong result. The this evaluation has to be done later, after you have added the particular solution. In this formulation we have assumed that none of the lambdas are identical, that is, we have assumed distinct roots. If some of the roots are repeated, okay, for example, let us say lambda square minus 4 lambda plus 4 equal to 0. If this is your characteristic equation, then obviously lambda 1 is 2 and lambda 2 is also equal to 2. That is a case of repeated roots. We shall see a little later how to tackle the case of repeated roots, okay. But as long as the roots are distinct, you can write it in this form. The particular solution yp of n, that is very simple to find out. Yp of n is of the same form as x of n, the input. In other words, if x of n is, let us say, a constant k, then yp of n shall also be another constant, let us say k1. If x of n is sinusoidal, then yp of n shall also be sinusoidal. That is, if x of n is, let us say, a cosine n omega 0 plus theta, then yp of n would be some other constant b cosine n omega 0 plus some other phase phi, okay. If x of n is, let us say, alpha to the power n exponential, then yp of n shall also be some other constant, let us say c alpha to the power n. So the particular solution is very easy to find. You assume with an unknown constant the same form as the given x of n. If x of n is k, then you assume it to be k1. K, of course, is k u of n, k1 u of n. Similarly, if it is sinusoidal of this form, then you assume two constants b and phi, okay, the same form as the input. If it is alpha to the n, then you assume c alpha to the n, ypn, and you substitute it in the given difference equation. That will find out the constant, the unknown constant or constants. There may be two constants, okay. The particular solution assumed form when substituted in the given difference equation shall give you ypn completely along with its constants. After finding that, you come back to the complementary function, add to the complementary function, then you invoke your initial conditions, okay. Let us take one or two examples. Before I take an example, suppose the roots are repeated, okay. Suppose in the nth order equation that we had, suppose the roots are lambda 1, lambda 1, lambda 1. Suppose one of the roots, lambda 1, is repeated L times, and then you have lambda L plus 1, lambda L plus 2 up to lambda Yes?
Plus n minus 1.
No, capital N. The total number is capital N. L of them are here. I start from L plus 1, so I go up to N. These are distinct, okay? If that is the case, then your particular solution yc of n would be equal to lambda 1 to the power n. Normally you would have a lambda 1 to the n plus b lambda to the n and so on, but since all of them are identical, you use some alpha 1 plus n times alpha 2 for the second term plus n squared times alpha 3 and so on, plus the last term would be n to the L minus 1 alpha L minus 1 plus how many constants have you used?
Alpha L. Alpha L. It will be alpha L.
No. We had a constant here. So how many constants have you used? L minus 1. But there are how many roots? L roots. So you must go up to, no, you don't go up to that. What is the problem? If one root, second, third, it should have been, pardon me? We started with 1 and this is L plus 1.
Sir, actually, lambda n shouldn't be there. Lambda n, if you have put last one is lambda n, then we have more number of positives.
How come? There are L here, L plus 1. How many are here? N minus L. So the number of roots is the same. Now you go up to n to the L minus 1.
Alpha L.
How many are here?
L minus 1.
L minus 1.
L minus 1.
L coefficients are.
It should be L minus.
Alpha L. Sir. It should be
Okay.
alpha L.
Alpha L. This is n to the L minus 1?
No,
Because we start from n to the power 0. Okay? Clear? Yeah, I wanted you to answer this question. Sometimes I will write wrong things intentionally to be corrected by you. Okay? I wrote it intentionally, alpha L minus. Plus, then what? Alpha L plus 1, lambda L plus 1 to the power n corresponding to this term, plus etc. plus alpha capital N lambda capital N to the power n. This will be the form of the particular solution. That is, in the case of repeated roots, you take the first term, second term must be multiplied by n, third term by n squared, and you go up to n to the power L minus 1. If a root is repeated twice, then you simply use alpha 1 plus n alpha 2. Okay? The power of n is 1 less than the number of repetitions. Okay? So this is in general the solution. Yes?
Particular solution is this complementary solution?
This is the complementary function. For the particular solution, you simply put y of n of the same form as x of n and find out what the constant is. That would be the complete particular solution. Particular solution should have no constant. Okay? Add that to this and then invoke the capital N number of initial conditions to find out the capital N number of constants, alpha 1, alpha 2 and so on and so forth. Let us take an example. We take y of n plus 0.5 y of n minus 1 is equal to 2 u of n. And the problem is to find y of n for n greater than equal to 0, you require, it's a first order equation, you require one initial condition, and it is given that y of n minus 1 equal to 2. So you try your solution. What is the solution? Lambda to the n plus 0.5 lambda to the n minus 1 should be equal to 2, and therefore lambda is equal to how much?
1.5.
What are you solving? Now I shall play this game a bit often, because this is the 5th or 6th lecture. 6th. Yeah, I want you to get used to SCDF. Now I am trying another trick. I have made a mistake here. The right hand side should be 0, because I am finding the complementary function. Right hand side should be 0, and this gives you lambda equal to minus 0.5. Then therefore the yc of n is of the form some constant k lambda to the power n. So minus 0.5 to the power n. I do not evaluate k by invoking initial condition. I first find the particular solution. To find the particular solution, I assume it to be of the same form as the given input. The input is a constant 2. So I assume yp of n equal to some constant k1. Substitute it in the original equation. The equation is y of n plus 0.5 y of n minus 1 equal to 2. So I substitute k1 plus 0.5 k1, y of n minus 1 is also k1, because it is a constant, equal to 2. So k1 is equal to 2 divided by 1.5, which is equal to, I believe, 4 by 3. 4 by 3. Is that okay? I don't write it as 1.3333 recurring. In a digital system, in DSP you must be careful. Maintain a fraction till you are forced to change it, because as soon as you make a truncation, you make an error. Truncation will have to be done because of finite word length. 4 by 3 cannot be represented by binary number, right? So you will make an error there. Why make an error in the design? In the calculation you keep the number as a fraction as long as you can. If it makes out into a let's say 1.73, you are permitted to do that, but if it's recurring, then you do not. Okay, pi keep as pi, exponential e keep as exponentially as long as you can. All right. So what we do now is y of n is equal to k minus 0.5 to the n, the complementary function, and I add it to 4 by 3. Then I put the initial condition, that is y of minus 1, initial condition, y of minus 1 is equal to 2 is equal to k minus 0.5 to the power minus 1 plus 4 by 3, and you can very easily show that k comes as minus 1/3. I hope I am right, this is my calculation, yeah. K comes as minus 1/3. Therefore, my final solution is, total solution is minus 1/3, 0.5 to the power n plus 4/3. You can write it. Pardon me? Minus 0.5, okay. I stand corrected, minus 0.5. So this is the solution. Now I am tempted to, I have another 3 minutes, I am tempted to take another example in which the input, a complicated example, input is of the same form as one of the eigenvalues. Okay, let's take this minus 0.5 to the power n u of n. Okay, now you have a problem. You have a problem. The input is of the same form as the eigen function of the system. Okay, lambda to the power n. In this case, what you do is the complementary function is the same. What is the complementary function? Y c of n is equal to k minus 0.5 to the power n, and y p of n you no longer assume as k1 minus 0.5 to the n, because it is an eigenfunction of the system. So what you do is exactly like repeated roots, you multiply by n and then put minus 0.5 to the n. Substitute it in this equation to find what is k1, and if you do that, I have done that, I will omit the calculation. If you substitute that, we get k1 as equal to 1, k1 as equal to 1, which means I am omitting the algebra, you can do that yourself, which means that my y of n is equal to k1 plus n, k1 minus 0.5 raised to the n is the complementary function, then n times minus 0.5 to the n is the particular solution. So, k1 plus n minus 0.5 to the power n, all right. And at this point you introduce the initial condition y of minus 1, same initial condition equal to 2. If you put this, then you get k1 minus 1 minus 0.5 to the power minus 1, all right. The right hand side is k1 minus 1. What is this? Oh, the first one is k, yes, I beg your pardon. This is not an intentional mistake, it is an unintentional one. Okay, it is k, k minus 1. What is this quantity? 2, negative sign I have taken here. So, this is equal to minus 2k plus 2. Our equation now becomes 2 equal to minus 2k plus 2. What does this give for k? K equal to 0. The complementary function does not exist. It is a very interesting problem, okay. But this is the correct solution. You can verify y of n is equal to n times minus 0.5 to the power n, okay. And I think we should stop here.